A person of 6 feet in height is walking towards street light or a street light along a street path at a rate of 3 feet per second. So what we see that there's a person and there is a street light. Let me draw it like this. The street light here and a person walking toward it. Say we have this person here. And the person is of 6 feet. And then this light or street light is of 18 feet above the ground. Let's draw the ground. This is ground and this is 18 feet. The person, let me draw it as the height from here to here. We have the shadow. The shadow comes from this light to the person, right? And the shadows the same here, this length. Let's call it X. So for example, this person is here, the shadows, this length. The height of the street light is 18 feet above the ground. What is the rate of in feet per second at which the person's shadow is shortening? Because this person is walking toward the street light. So for example, at some moments they are here. For example, at one point they are here. They're walking toward it. So they are here, then the shadows will be then, I draw the line between the head of the person. So I connect this. The shadows, now this length, you see that obviously here, it is indeed shorter. This one is shorter than this one. Now we need to find the rate of change. You are asking for the rate of change for the length of his shadow, not the rate of change for the distance from the tip of the shadow to the bottom of the street light. So we are really asked about this dx over dt. What is the rate in feet per second at which the person's shadow is shortening? Okay. So this is what we need to find. We know a few data. The first one is this length is 18. Second one is this length is 6. And we know that walking toward a long straight path of 3 feet per second. So we know that the speed is 3 feet per second. Now let's call y the distance between the street light to the person. Let's call this y, this distance. Then we know that the speed of this person is 3 feet per second. So this means that y is getting shorter and shorter at the rate 3 feet per second. dy over dt is minus 3. Because this one getting shorter and shorter, that's why I put a negative here. The distance here is shorter and shorter. That is what we know, and that is what we need to compute. Now to compute dx over dt, we need to set up the relation between x and y. Here how we can do it. We have two right triangles. The first one, this one. The second one is this one. So if I consider the yellow right triangle and the bigger right triangle, they are similar. So we know that x divided by the length of this yellow right triangle x here divided by the length of the bigger one, which is x plus y, must be equal to this length over this length, 6 over 18. We got the relation, which is 1 over 3. So we know that x or 3x equal to x plus y, and multiplies this one, 3x equal to x plus y times 1. This one gives us 3x minus x, 2x equal to y. Now we can do derivative both sides, and with respect to t, the time, d over dt of the left hand side equal to d over dt of the right hand side, which is dy over dt. 2 times dx over dt equal to dy over dt. Now dy over dt is given to us, minus 3. So we know that this is minus 3, and therefore dx over dt minus 3 over 2. So this means that the shadow dispersion is shortened at the rate. We are doing shortening, so we know that it shortened 3 over 2 feet per second. Conclusion: the shadow is shortening at the rate 3 over 2 feet per second.